Welcome to this lecture series in complex numbers. In this lecture, we'll be looking at roots of unity, and let us recall some relevant things. So we saw the notion of nth roots earlier. If z0 is a complex number written in the trigonometric form, so r is a positive or a non-negative real, and theta is some angle, then all the nth roots of z0 can be expressed in this way. So the modulus is this number, and these are the arguments. So for k varying in this range, we get all the distinct, all the nth roots, in fact. All right. So let us now define what is the root of unity. So fix a positive integer, and nth root of unity is a complex number z, such that z to the n equals 1. So it's just z0 is being replaced by 1. 1 is also called unity, and therefore root of unity rather than root of z0. That's it. It's not a new concept in some sense. All right, so that's the definition of an nth root of unity. A root of unity is an nth root of unity for some positive integer n. So that's so we define nth roots of unity, and then we define roots of unity just as any complex number whose some positive integer power becomes equal to 1. Very simple. Note that every root of unity has modulus 1. So that's trivial, because if you take modulus on both sides, you get mod z to the n equals 1, and that forces that mod z is equal to 1. Okay. So there's a very nice geometric picture in which you can represent all the nth roots of unity. Here I have taken n equals 9. And this is the unit circle. So by that I mean all the complex numbers whose magnitude or modulus is 1 is this white circle. This is the complex number 1. This is, I'll call this complex number zeta, which is cos of 2 pi by 9 plus iota sine 2 pi by 9. So that's in some sense a principal nth root of unity, or whatever you want to call it. This is kind of the first non-trivial one that you get. And all the pink ones, all the other ones are also roots of unity. So these pink points are precisely the 9th roots of unities. So this angle is 2 pi by 9. And this angle is twice of 2 pi by 9, then thrice of 2 pi by 9. So basically these points become zeta square, zeta cube, zeta to the 4, zeta to the 5, zeta to the 6, zeta to the 7, zeta to the 8, and 1 is coming back to the zeta to the 9. So it kind of periodically cycles around. And it is important that we realize that it is actually the square of this guy, because what is this guy? This guy is cos of 4 pi by 9 plus iota sine 4 pi by 9, and hence it is just the square of this guy. De Moivre's theorem or whatever. Okay, so that's a picture that we should keep in mind. And now let's look at a special example, which is cube roots of unity. So basically roots of this equation, all the complex numbers satisfying this equation. So this is 1, this is omega square. These are the 3 roots of unity. Typically omega is used to denote this, this number, which is, the angle here is 2 pi by 3. So omega, if you calculate, turns out to be minus half plus root 3 by iota root 3 by 2. And omega square turns out to be minus half minus iota root 3 by 2. So these are, the 2 non-real roots of unity. Basically, one is of course a root. So 1, omega, and omega square are the 3 roots. And you can calculate their sum, 1 plus omega square, in 2 ways. This turns out to be 0. One reason is that, well, you can just add. If you add omega with omega square, you get minus 1, and then if you add 1, you get 0. So that's a way to see that this is 0. But another way would be you consider this polynomial z cube minus 1. uh, the coefficient of z square is 0, and the sum of roots, as we saw in Viete's theorem, the sum of roots is the coefficient of z square divided by the coefficient of z cube with a minus sign. But the coefficient of z square is 0, so this is 0. So there are at least two ways to see why this is 0. Even geometrically, it's quite clear because these three vectors, they are equi-spaced. So if you add these three things, you should get 0. They form vertices of an equilateral triangle. Anyway, also note that omega and omega square are the two roots of this particular polynomial, because z cube minus 1 is z minus 1 times 1 plus z square. 1 is already subsumed in this part, so the roots of the remaining part must be the other two roots, meaning the root except for 1. So omega and omega square are roots of this, or you can just calculate. We know how to find roots of a quadratic. There is a formula. So if you just calculate, you'll see that omega and omega square are the roots of that guy. So that's just a note. All right. And finally, this is a general remark. We have seen this in the case n equals 9, but here is the general remark. Fix a positive integer. Define zeta as that particular complex number. Zeta, of course, is an nth root of unity. But the point is that these are all the nth roots of unity. Once zeta is a root of unity, you can see that zeta square and all powers of zeta are also roots of unity. But the point is that these are all pairwise distinct. That you can easily check, because if suppose, for instance, zeta to the I were equal to zeta to the j for some I and j in this range, then you would see that zeta to the power j minus I is 1, and that won't happen unless j minus I is a multiple of n, and therefore you can show that these are all pairwise distinct. But anyway, I'm sure you see what's going on. And the sum of all the roots, again, either you can add it using the geometric series formula. It's a finite sum, and the geometric series formula applies equally well to complex numbers. Basically, this is equal to the first term times the common ratio power, the number of terms, minus 1 divided by common ratio minus 1. But what is zeta to the n? Zeta to the n is equal to 1, and hence this is 0. So that is one way. Or you could just think of this equation, zeta to the n minus 1 equals 0, or just this polynomial. This is a polynomial all of whose roots are these numbers, 1, zeta square, and so on. So the sum of roots by Viete's theorem should be the coefficient of z to the n minus 1 with a minus sign divided by the coefficient of z to the n. But the coefficient of z to the n minus 1 is 0, and therefore this is 0, so that is another way. This is what we did in the cube roots of unity thing. So that's it. That's all that I want to show. Or maybe, okay, let's do this one problem, this one example. So fix a positive integer, and these be all the nth roots of unity. So again, let me just emphasize that by zeta we mean cos 2 pi by n plus iota sine 2 pi by n. So now what we want to show is that this product, this horrible looking product, is actually a very nice real number. And let me do it in a slick way and point out another way to do it later. But first, here is one way to do it. So we have z to the n minus 1 equal to z minus 1 times z minus zeta square dot z minus zeta to the n minus 1. Why is that? This is what we saw in the polynomials lecture, that if you have a polynomial and you know all the roots of it with repetitions, then suppose f was my polynomial, then fz is equal to some constant times all these things, z minus zn. So if this is an n degree polynomial, then fz can be written in this fashion, where this is basically the leading coefficient, meaning the coefficient of z to the power n here, right? And that is what we are doing here. The coefficient of z to the power n is 1, so there is a 1 here, and these are all the roots, 1, zeta square, and so on. These are all the roots. So now all we do is we substitute 5 in place of z on both sides. So we get 5 to the n minus 1 equals 5 minus 1, 5 minus zeta, 5 minus zeta square, 5 minus zeta to the n minus 1. And that shows us that 5 to the n minus 1 divided by 4 is equal to what we wanted to calculate. Right, this is basically, we took this down, that's all. So that is one way. The other way is the following. Define fz as z to the n minus 1. All right. And then define gz as follows. So gz would be f of, what should I write? So this should be f of 5 minus z. So if we define it that way, this is of course a polynomial, g of z. When we define g this way, this is a polynomial. And the roots of this polynomial are precisely, so the roots of g are roots of g are 5 minus 1, 5 minus zeta, 5 minus zeta to the n minus 1. Why? Because if we substitute any, let's say 5 minus zeta to the I in place of z here, then that is just f of zeta to the I, which is 0. So this is a degree n polynomial because f is a degree n polynomial, and we have found n roots of it, and therefore these are all the roots. These are all distinct, and hence these have to be all the roots. What we are asked is product of all the roots of g, except for this particular one. But well, what we know how to calculate is product of all the roots using the Viete's theorem. So using Viete's theorem, calculate the product of all the roots. We get this product: 5 minus 1, 5 minus zeta square, 5 minus, let me write that again. So 5 minus 1, 5 minus zeta, 5 minus zeta square, and dot 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 5 minus zeta to the power n minus 1. This we can calculate by finding the corresponding, the correct coefficient here. And since this is just a number, we divide that and we'll get the same answer. So that is another way. Just create a polynomial whose roots are these guys along with 5 minus 1. And that polynomial is very easy to construct. This is the way to construct it. And that's it. But yeah, this is very quick. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.